Okay, in this lecture, we're going to look at how Slide does reliability analysis for us. So I've set up a model that shows our typical little levee here. I won't include groundwater or anything because you can add those features if you want to. I just want to focus on the reliability part. So we can go to Analysis and Project Settings, and then you'll see a Statistics button here on the left side. So if I click that, there's two things here that you can click. One is sensitivity analysis. So sometimes we're interested in knowing how uncertainty in one parameter results in uncertainty in the factor of safety. So what the sensitivity analysis will do is vary each parameter by plus or minus some fixed range that you can set. And then it'll plot factor of safety versus each parameter. So you can see what's really driving your analysis. It can be really useful for figuring out which things have the most influence on factor of safety and where you might want to invest your time in refining your understanding of the problem. But what we're going to do here is probabilistic analysis. Okay, and then I'll explain a little bit about what these what these fields are. So there's Monte Carlo simulation, and we've talked about that in the previous lecture. What Monte Carlo simulation will do is just randomly sample the random variables that you specify and compute or approximate probability of failure based on the number of cases that have a factor of safety less than 1 in this case, or the number of cases where the demand is higher than the capacity, the load is higher than the resistance. It turns out that just doing total random sampling is not the most efficient way to do a Monte Carlo simulation. So there are these other methods that involve importance sampling. So I'm going to click the Latin hypercube method. This is a method of figuring out how to adjust your random samples so that you're really only sampling the space that you're interested in, which would be near a factor of safety of 1. And that can give you more resolution for the probability of failure for a given number of simulations. And then number of samples, it's going to do 1,000 here. 1,000 is really not very many, but I'm going to leave it set to that number, and we can see what we get out. Then here is a spatial variability analysis, and you can have Markovian 1D separable, or Gaussian. This is about how the soil properties might be spatially correlated with each other, and we'll talk about spatial correlation later. Actually, a lot of the time, the uncertainty in something like undrained strength, if you went out to a site and measured undrained strength at a whole bunch of different spots within the site, you would get a mean and a standard deviation and maybe some distribution function of those samples of undrained strength. It turns out that probably what you're measuring is actually spatial variability rather than uncertainty. Uncertainty would be how well do you know the undrained strength at a point. And to get that, you would have to sample the same point over and over again and do a bunch of lab tests to figure out that distribution. It'd probably be pretty narrow bands. You'd probably get a pretty small standard deviation. So anyway, I think a lot of the time we mix uncertainty with spatial variability, and those are different things. Down here, these analysis type, there's two options. And this is pretty important because global minimum and overall slope are the two different approaches. Global minimum will run pretty fast. So what global minimum does is does first a deterministic analysis. So all the input parameters are set to their mean value, and it figures out the critical failure surface. So it'll analyze 5,000 surfaces and give you the minimum surface. Then after it's found that surface, now it will vary the material properties and get you a probability of failure. Of course, the problem is that when you change the material properties, the critical failure surface changes potentially too. So global minimum is not super accurate because it's using the same failure surface as it starts varying the properties. Overall slope will repeat the 5,000 slip surfaces or however many you specify for each of these 1,000 Monte Carlo simulation samples. So that's already 5 million calculations that it has to do, which is a lot. So I'm going to stick with global minimum. Overall slope does take longer to compute. It says here several minutes to hours. So for this demo, we'll just do global minimum. All right, now when we go to our material properties, there's two things. There's material properties and statistical properties. So let me go in here to material properties. Let's see, I think we've been doing 5 kPa and 30-degree friction angle for our material properties, no water surface in this case. Okay, and then there's 2 ways to get to statistical properties. I can just click the statistics button down here, or I can go here and do statistical properties. They'll both take us to the same place. So for material 1, we can add now all of the parameters that we think are going to be random variables. So you can do cohesion, friction angle, and unit weight. Let's do all 3 of those. And we'll just pick normal distribution functions for all of them. You can change them later. So you can do a uniform distribution. That's where the probability density is just constant. Triangular, a beta distribution, exponential, log normal, and so forth. Okay, what I'm going to do, the mean value of the cohesion is 5. The standard deviation, I'm going to set it to be 2. There is the option too of using a coefficient of variation, in which case you can just put in a coefficient of variation for the strength parameters, and 0.2 would be the mean divided by the standard deviation, and now it's going to make it log normal. So there's different ways of doing it. I'm going to uncheck that, leave it at 2, and then relative minimum. This is how far below and above you want to truncate the normal distribution function. So one problem, if our mean is 5 and our standard deviation is 2, then you only have to go 2.5 standard deviations below the mean, and all of a sudden you have a negative cohesion. Okay, so for normally distributed random variables, sometimes you have to truncate things. So I'm going to put 4 right there, and then the relative max, I'll also put 4. So we're doing a truncated normal distribution function now. For the friction angle standard deviation, let's put it in as 5. And then unit weight, let's do 3. Now for these, I'm not going to put a relative minimum or max. It'll just do the full range. Because these are having a small coefficient of variation, right? The standard deviation relative to the mean is pretty small. So I'm going to put, and then there is correlation. So, okay, you do have to put numbers in here. So I'm going to put them in as being 30 and 30. And then this one, 20 and 20. That way it's using just the full range. Didn't like that 20. Let's click on correlation. So you can apply correlation between the cohesion and the friction angle in this case. And we already know there's correlation between unit weight and undrained strength because we did that example problem, and that's a positive correlation. It turns out that cohesion and friction angle have negative correlation. And the reason is really pretty basic. Like if you had a set of more circles, say you have 3 circles, you could fit those circles with like a least squares line that would be the best fit, and it would have a certain cohesion and friction angle. Well, you could also slightly increase the cohesion and slightly decrease the friction angle, and it would fit almost the same. Similarly, you could decrease the cohesion and increase the friction angle, and it would fit almost the same. So for a given set of circles, for a given laboratory test, you're going to get negative correlation. I'm going to leave this as just no correlation. We'll leave them uncorrelated. We can add that in later to see what it looks like. Okay, then we need to go to project settings, methods. I'm going to use Spencer's method. Okay, and then surfaces, we'll do circular, grid search, auto grid. And now we're ready to go. I'm going to calculate this. Oh, I need to save it first. Call it reliability example. All right. So it's done the calculation for us here. And when we go to the interpreter, we get a few extra things. Before we just got factor of safety. Now what we get is a deterministic factor of safety of 2.127. So what that means is that if you didn't do any statistical analysis and you just put in the mean values or the baseline values for each parameter, the factor of safety would be 2.127. Okay, the mean of the factors of safety is 2.155. So what that means is that it ran 1,000 Monte Carlo simulations, and the mean factor of safety from those 1,000 realizations was 2.155. Okay, and then the probability of failure is 0. So we haven't done enough simulations to get a reliable probability of failure in this case. And the reliability index, if the reliability index is normal, we get 2.987, so almost 3. And we know that if we have a normally distributed margin of safety, a reliability of index of 3 would give us a probability of failure that's like 0.001 or something. So what I'm going to do is go back and go to project settings, statistics, and we're going to do 10,000 Monte Carlo simulations. Push OK, calculate again. So it didn't take that much longer. Now we should have, I hope, well, the probability of failure still comes out to be 0.000. So out of those 10,000, none of them actually have failed. Let's project settings. I'm going to try 100,000. It could be the case that our margin of safety is not normally distributed, in which case it could be that the probability of failure actually is really low. Okay, it's still 0. So the reliability index is pretty consistently coming out to be 2.987 if the margin of safety were normally distributed, and it's coming out to be 4.225 if it's log normally distributed. So maybe our reliability index looks more log normal. Now there are some features that we can look at in the statistics. Scatter plot, convergence. Okay, so here's a cumulative probability function for cohesion. And you can see it's going from a value of 1 all the way up to a value of, what is that, 9.5 or something like that. So this is in accordance with the probability density function that we specified. And let's see. Go back to the basic thing. Sorry, you can probably hear my dog barking. Let's go back and adjust the parameters here. So statistical properties. I'm going to make the standard deviation for the friction angle a little bit higher, right? And let's run this and see. Go ahead and save it. We'll run it. I'd like to get something that gives me a probability of failure that's bigger than 0. Just to illustrate. Okay, it's still coming out to be 0, which makes me wonder if it's actually varying. Friction angle. Okay, so the friction angle is varying indeed. Let's just lower the mean value just to illustrate what happens here. So instead of 30, actually let's make it so that the factor of safety is 1.5, because that's a common factor of safety that we target. So I'm going to put in 25 degrees for the friction angle. Okay, now that I've changed the baseline, I have to go and change the range on the statistics to be 25. Okay, now we can run it. and our factor of safety is 1.8. So I actually need to reduce it a little bit. I want to get it down to 1.5. Here, we'll go statistics. Let's put a mean of 20, standard deviation of 10, and then we'll go 20 and 20. There we go, 1.53. So the range that I put in here for the standard deviation is actually fairly reasonable. And in this case, we get a deterministic factor of safety of 1.53. But the probability of failure is 15.6%. It's a pretty high probability of failure, right? That might be a surprise because the factor of safety is 1.5. That's what we design slopes for. Yet the probability of failure is pretty high. So if we go back here and look at our statistical properties, okay, we put in maybe the standard deviation's a little big, right? So 20 degrees. Let's do the coefficient of variation method. A coefficient of variation is the standard deviation divided by the mean. And that's a common way for us to specify strength parameters for soil properties. 0.2 is kind of low, maybe 0.3. It depends on depositional environment and some other things. And I'll provide some literature that provides kind of some typical values of coefficient of variation. I'm going to put in 0.3 and then run this calculation. And I'm doing this just to show you that there are different ways of getting the probability of failure and specifying these input parameters. And now we're getting pretty much the same probability of failure that we had before. And if I come in here and decrease this coefficient of variation to 0.2, the mean values have all stayed the same. Our deterministic factor of safety should stay the same, but our probability of failure should now go down. So let's take a look. Probability of failure stayed the same. I'm worried that the interpreter is not updating. Okay, yeah, the interpreter wasn't updating for some reason. So our probability of failure has now gone down to 2% just by adjusting the uncertainty in the input parameters. So you can see how the uncertainty doesn't change our factor of safety. It does change our probability of failure. So it makes sense that uncertainty should have an impact on our selection of how safe we need to be, right? If something is highly uncertain, we might want to make it stronger or do something so that we're pretty sure it's not going to fail. Now, how much is pretty sure? I mean, that takes some judgment. But anyway, you can adjust things to get a probability of failure that is low enough for a particular problem. And we'll leave it at that because there's a lot more to it than what we can cover in this lecture.